Okay, so when we mix solutions together and form a precipitate, we can write balanced chemical equations because a chemical reaction is occurring in the formation of that precipitate. So solubility and precipitation reactions have very specific chemical equations. And we can break those down into 3 different types of chemical equations. The first one is a molecular equation. In a molecular equation, compounds are represented by chemical formulas as though they exist in solution as molecules or formula units. Now we know that if they're ionic and soluble in water, they are not actually existing as those molecules, but it's a nice way to show what the reaction is happening. So, reactions in which cations in 2 ionic compounds exchange anions are called metathesis or double replacement reactions. So we typically call this double replacement because we're replacing 2 portions of this reaction. So let's look at the example I have here on the screen. So we have sodium sulfate and barium hydroxide react to form sodium hydroxide and barium sulfate. So we can see that all we did in this reaction is switch those anions, right? We said that we have anions in solution. We have Na plus, SO4 2 minus, Ba plus, OH minus, plus 2, sorry. So when they're in solution, they are going to switch their anions. So they exchange their anions. So because it's happening between 2 species, we call this a double replacement reaction. So our new equation, I have this written wrong, this should be OH minus, there we go. Our new equation is now sodium with hydroxide, and barium with sulfate, BaSO4. Okay, and you can see that we've written their formulas to account for their charges correctly. We're using our typical rules for writing ionic compounds. Okay, so all we did was switch our anions. Now, because these are ionic compounds, we're never going to have sodium going with barium because those are 2 cations that are attracted to each other. That's not going to happen. And we're also not going to have the sulfate attracted to the hydroxide because they're both anions. So that will also not happen. So we are able to predict the products of this reaction simply by switching those anions. Now I'll make a note that we have to remember that the charges on ions in a compound must sum to 0. So make sure that you have written correct formulas for the products. So when we're writing out our products and switching our anions, that you've written out the correct formulas for the products and that each of the equations you have written is balanced. And we'll talk about balancing here in a second. If you find that you're having trouble balancing an equation, check to make sure that you have correct formulas for the products. And we'll walk through a few examples to show what we mean by that. So, we have some steps for writing our molecular equations. And I have a specific example here. It's the reaction between aqueous lead 2 nitrate and sodium iodide. So what we want to do first is write the formulas for the reactants. And we don't want to forget their states. So we know that these are going to be aqueous. So we're going to have an AQ because they are dissolved in water. So we have lead 2 nitrate. So we have lead 2, Pb2 plus, and nitrate, NO3 minus. So in order to form a compound, we have Pb and O3 2. Okay, so I had to balance out my charges appropriately. If you don't remember our specific rules for ionic compounds and our polyatomic ions, please go back and review chapter 5. And this has an AQ as its state. We add to that as a reactant sodium, Na plus, and iodide, I minus, to create the formula NaI with aqueous. Our next step is to write the formulas for the products by trading our anions. So we have PbNO3 2 aqueous reacting with NaI aqueous. And now what we're going to do is swap out our anions. So I now have lead with iodide, so we have to look at our charges for that. So Pb2 plus and I minus would become PbI2. And then we get sodium with nitrate, so we get NaNO3. So I'm still following my rules for ionic compounds, making sure that my formulas of my products are properly balanced to account for the charges. Okay, so now we want to balance the equation. We're going to use our rule of keeping our polyatomic ions together in these when we're balancing these. So we have PbNO3, Na, and I. So we have Pb, we have 1, nitrate we have 2, sodium we have 1, iodine we have 1. Then we have lead on our product side, we have 1, we have 2 iodides, we have 1 sodium, and 1 nitrate. So we can start from either iodide or nitrate, it doesn't really matter. Let's put a 2 in front of our sodium nitrate. That balances out our nitrate, it misbalances our sodium. So now, we have lead balanced, nitrate balanced. Now let's go to our reactant side and try to balance our sodium and our iodide, which are in the same molecule. So if we put a 2 in front of sodium and iodide, that balances them out. Okay, so once we have the balanced equation, we have one more step to do, and that's to predict if a precipitate is going to form from this reaction, from our two products. Is a precipitate going to form? So let's take a second and let me rewrite our balanced equation. So we have PbNO3 2, which is aqueous, with 2 sodium iodides, also aqueous, react to form PbI2 plus 2 sodium nitrates. So we need to determine what our states of matter are going to be on PbI2 and sodium nitrate. Okay, so what we're going to do is take both of those products and determine if they are water soluble or water insoluble. So we have lead iodide. So iodide is here. It's typically soluble in water unless it's with silver, copper, mercury, or lead. So because we have lead iodide, we fall into our insoluble exception. So if this is insoluble, the reaction forms a solid. So we put a solid notation as our state of matter because we formed a solid. The lead iodide is present in the reaction vessel as a solid rather than as its ions in solution. We can next look at sodium nitrate. We know nitrate is always soluble, and as is sodium. Okay, so we have two soluble components in there. So sodium nitrate is not going to form a solid, so this gets the AQ notation because it is remaining as its ions in solution. Okay, I'm going to copy this because we're going to need this for later. Okay, So let's continue to practice this. The main thing that we have to practice with these types of problems is swapping our products, or swapping our anions to form our products, balancing the equations appropriately, and then determining what our solid and what our aqueous products are going to be, if any. Because if you get that part wrong, then the rest of what we're going to do is not going to be useful. So here we have silver nitrate and sodium sulfate. So what we're going to do is we're going to swap our anions. So if we look at our ions in solution, we have silver plus, NO3 minus, sodium plus, and SO4 2 minus. So when I put silver with sulfate, I'm going to get Ag2SO4 because of the 2 charge and the 1 plus charge. We have to account for that in those. And then for sodium and nitrate, they have equal but opposite charges, so I just need NaNO3. Okay, we can balance these now. We have Ag, NO3, Na2, Na, and SO4. So I'm keeping my polyatomic ions together. Silver, I have 1 and 2. Nitrate, I have 1 and 1. Sodium, I have 2 and 1. And sulfate, I have 1 and 1. So let's try to balance our silver. Let's put a 2 out in front there. So 2 silver nitrate. That changes this to 2 and the nitrate to 2. We can now try to balance our sodium and our nitrate by adding a 2 out in front on our product side. So we have 2 of those. If you're still getting hung up on the balancing of chemical equations, I strongly encourage you to go back to Chapter 8 and review balancing chemical equations, do the practice that we have on our lecture slides, as well as go back to our online simulation to practice balancing equations. Okay, so there's our balanced equation. The last thing we have to do is determine what is soluble and what is insoluble. So let's look back at our chart. We have silver sulfate. So let's see. Silver sulfate. So we have sulfates here. So it's typically soluble, but we have silver as one of our exceptions. So we're into our exceptions, so this would be a solid. It's water insoluble. It prefers to be in solution as a solid rather than its ions. And then we have NaNO3, which was our example before. NO3 and Na are both water soluble. So that's going to be AQ. So our precipitate in this reaction is going to be silver sulfate. Okay, let's try the next one. Okay, we have ammonium carbonate and calcium chloride. So we are going to swap our anions here. And we are going to have, let's see, we have NH4 plus, CO3 2 minus, Ca 2 plus, and Cl minus. Remember, all of those charges come either from the periodic table or from the polyatomic ion charge itself. So when I do ammonium with chloride, that's going to be NH, oops, that should have a 4 on it, NH4Cl, they're in equal but opposite charges, plus CaCO3, equal but opposite charges as well. Okay, next up is to balance. So we have NH4, we have CO3, we have Ca, and we have Cl. So I have 2 NH4s, 1 CO3, 1 Ca, 2 Cls, 1 NH4, 1 Cl, 1 carbonate, 1 calcium. So I have to balance that ammonium and that chlorine. I think all I need is a 2 here to balance that out. That's our balanced equation. So our next thing is to determine what is going to be our solid and what is not. So we have NH4 and Cl. NH4 is water or soluble, as is Cl. So that's going to get an AQ to show that it is going to remain as its ions in solution. Then we have CaCO3. Let's see, carbonate is over here. Carbonate is typically insoluble in water. The only exceptions are group 1 and NH4. Well, calcium is not in group 1, it's in group 2, and it's no longer paired with NH4, so that would make this water insoluble. So that would get the solid notation for its state. So by mixing those two solutions of ammonium carbonate and calcium chloride, we would get a precipitate that forms, and that precipitate would be calcium carbonate. Okay, so our next step to our solubility equations and our precipitation reactions is writing the ionic equations. So in an ionic equation, compounds that exist completely or predominantly as ions in solution are represented as those ions. So here we have our example from previous, where we had sodium sulfate and barium hydroxide, but instead of showing those aqueous compounds as one unit, we're separating them into their individual ions and properly accounting for their charges as well as any balancing that was needed. We do this on both the products and the reactant side, and anything that is a solid is going to remain as a solid. We can also have it where it remains as a liquid if water is actually what's being formed. There are some cases where water does form as a product of that reaction, and that would remain as H2O. So only anything that has AQ, so we're looking for these AQs here. What did I think? I had a highlighter. Anything with AQ we would represent as its individual ions. So let's continue with our previous example. Let's see, let me paste what we had before. So there was our example of lead nitrate and sodium iodide. So here's our balanced equation. We said that lead iodide is going to form our solid. So our ionic equation for this would be all three of these compounds we would represent as their individual ions in the reaction. So I'm going to get up nice and close to write nice and small because we have to account for balancing the individual ion and their charge as well as their specific state. So let's start off. We have lead nitrate. That's going to break up into lead ions, Pb2+. The lead ions are aqueous in solution. We then have nitrate, NO3-, that's also aqueous. Because there's a 2 subscript on that NO3, I'm going to bring that up as a stoichiometric coefficient. Okay, I can't write this as parentheses 2. I can't write that. I have to use the 2 as a stoichiometric balancing factor. Next up, we have NaI, sodium iodide. We're still going to use that 2. It's going to apply to the sodium ions and the iodide ions as well. So we're going to have 2 Na plus AQ and 2 I minus ions AQ. So that's our reactant side of our ionic equation. I've shown each ion as its ion, each compound as its individual ions, all with their charges, all with stoichiometric balancing factors that come from our previously balanced equation, and all with their aqueous states on them as well. These are all required when you have to write these equations out on your homework and your exams, balancing charges and states. So now we move to our product side. PbI2, lead 2 iodide, is a solid. So in the ionic equation, it remains as a solid. because the ionic equation only shows the pieces that are ions in the solutions. So lead iodide is not going to be its ions in solution, it's going to remain as a solid. So we keep that one as is. We then have sodium nitrate. So again, the 2 goes to the sodium and to the nitrate. So we have 2Na plus AQ plus 2NO3 minus AQ. Okay, that is our completed ionic equation for this example. You'll see that it is still balanced. Okay, I have 1 lead, 2 nitrate, 2 sodium, 2 iodide, and 2 iodide. Okay, some of them may be in different forms, such as the lead and the iodide, but it ends up working out. Okay, our charges are all balanced and everything like that. So it doesn't matter what order you show them in on either side. Okay, if you decided to put the ions first and the lead 2 iodide last, that's totally fine. As long as they're on the right side of the arrow, you're good. So some tips that I have for writing these ionic equations. The first one is the obvious one, to keep our polyatomic ions together because they are in solution as those ions. Okay, and the next is to use your subscripts and your stoichiometric factors to balance. So we did that twice. We said that this 2 should come down as a stoichiometric factor, and the stoichiometric factors that we use to balance can be applied to those individual ions. Okay, so our ionic equation also has to be balanced. All of the equations that we're writing have to be balanced. Let's continue with our other 2 examples that we had from our previous molecular equations. So give me 1 second, I'm going to rewrite those equations and then we can write the ionic equations from that. I've written out our balanced molecular equations from our previous examples for both of these problems. So now we can utilize these to write our ionic equations for both of them. So let's go in. So we're going to write anything that has an AQ on it as its individual ions and using those subscripts and those stoichiometric factors to balance. So our first example, we have 2 silver plus AQ plus 2 NO3 minus AQ. So that 2 gets applied here and there. Next up, we have 2 sodium plus AQ. So my 2 from sodium came up here, okay? Plus SO4, 2 minus AQ. So that's my reactant side. Everything is represented as an ion. Our reactants are always going to be all ions. We're never going to start with a precipitate. And on our product side, we have 2 Na plus. That 2 is going to the Na as well as to NO3. And I think I ran out of room, but luckily it's just for my solid. So silver sulfate stays as a solid in the ionic equation, so we just keep it as Ag2SO4 solid. So even though we're writing things as their individual ions, we have to remember that we're still forming a solid, so you still need to show the solid in your ionic compound. Okay, now what I want you to do is try writing the ionic equation for our last example here. Okay, everything with an AQ should be written as its ions. If it's a solid, it stays together. So take a second, pause your video, and write out the ionic equation for this last example. let's jump into our ionic equation for our last example here. We start off with our two aqueous reactants. We have NH4 plus AQ, and it needs a 2 out in front to balance it out. We add to that CO3 2 minus with an AQ, so that's our first reactant. We then have Ca2 plus with an aqueous and 2 Cl minus with an aqueous. We then go to our product side where we have CaCO3 remaining as a solid, and then we have 2 NH4 pluses AQ plus 2 Cl minuses AQ. And we can see that this is still balanced. I have 2 Cls, 2 Cls, 2 NH4s, 2 NH4s, 1 Ca, 1 Ca, 1 CO3, 1 CO3. So we are completely balanced. And that is our ionic equation for our last example. Now we're going to use these ionic equations in one additional step. So we're going to use them to make our net ionic equations. An equation that includes only the species that are actually involved in the reaction is called the net ionic equation. So we only show the ions that form the products. So ions that appear on both sides of the equation are called spectator ions. So in our example of sodium sulfate and barium hydroxide, we formed barium sulfate. The sodium ions and the hydroxide ions did not participate in that reaction. The only ions that participated in that reaction were the barium and the sulfate. So you can think of this like a math equation. If you had the same variable on both sides of your equal sign, it would cancel out. The same thing can apply to ions. Because they are the same on either side of the equation or of the arrow, think of the arrow like the equal sign, they can cancel out. Those are your spectator ions. Like in a football game, the spectators are on the sidelines cheering you on, but they're not actually playing in the game. The pieces that are playing in the game are the ones that are forming the precipitate. So we write our net ionic equation that shows only the ions that participate in the formation of the solid. So our net ionic equations always have the same setup where we have ions on one side and solid on the other. Okay? So let's write the net ionic equation for our example from previous. Here is our net ionic equation from our previous example of lead nitrate and sodium iodide reacting to create lead iodide and sodium nitrate. So we have to look at what ions are the same on both sides. Well, we have nitrate and nitrate that are the same, and sodium that are the same, so we can cancel those out. Whatever is forming your aqueous product is going to be your spectator ions. Okay? Because the other product is going to be your solid. So our net ionic equation for this, I'm going to write it in a different color, is going to be lead 2 plus ions that are originally aqueous react with 2 iodide ions that are aqueous and create the solid lead 2 iodide. So our other product was sodium nitrate, and those became our spectator ions. So here is our net ionic equation for this reaction. So essentially what we've been doing is breaking down the equation further and further from these three different steps in order to isolate the specific ions that are creating the precipitate in these precipitation reactions. Let's continue on with our previous examples as well, and let's take our ionic equations from these and write out our net ionic equations. Here are the ionic equations that we did previously. So what we want to do is determine what our spectator ions are and cancel those out, and then isolate the ions that are forming our solid. So our solid in our first one is silver sulfate, so that means sulfate and silver are participating in that, and we can see that sodium and nitrate are the same on either side of the arrow, so they get canceled out. So our net ionic equation is 2Ag plus, originally aqueous, plus SO4, 2 minus, originally aqueous, combined to create Ag2SO4, which is now a solid. And we can see from this net ionic equation that it is balanced because we know that we needed 2 silver ions to mix with 1 sulfate ion to have a net neutral charge on that product. So for our last example here, what I want you to do is determine what the spectator ions are, cancel them out, and then write the net ionic equation for the formation of the precipitate in our last equation here. We can see from our molecular equation that our aqueous product, NH4Cl, those are going to be our spectator ions because our aqueous product are the spectator ions. We see that here as NaNO3 as well. So we can cancel out the NH4 and the Cl's on both sides. And what we're left with are the ions that are participating in the reaction. So we have CO3, 2 minus, aqueous, plus Ca2 plus, aqueous, going to CaCO3 solid. Now the typical thing is to have the cation first. So typically we would have the cation first, and then the anion. I personally don't care, but sometimes Alex is a little picky about that, so just watch out for that when you're writing out your net ionic equation. They may have specifics on what order they want. I personally don't care because it shows the same thing. So let's just review overall what these precipitation reactions are having us do. We have to write out 3 different equations. We have to write out the molecular, the ionic, and the net ionic equations. So the first thing we have to do is write and balance the molecular equation, predicting the products by assuming that the cations trade anions. So that's our double replacement. Okay. Once we've traded those, we have to remember to balance it and predict the products. And what isn't written here is to predict our precipitate. That's the big part of this. If we're talking about precipitation reactions, we better see if a precipitate forms. We then want to write out the ionic equation by separating your strong electrolytes, so that's anything with an AQ, into their constituent ions. So separate anything with an AQ into its individual ions. And here we're going to keep our solid together. So if we formed a precipitate, it gets a solid notation because it is now a solid in solution. So we keep that solid together. It's no longer its individual ions. Once we have that, we want to write the net ionic equation by identifying and canceling our spectator ions, which is going to be whatever our aqueous product is. and we're going to cancel them out on both sides. And what we'll be left with is the net ionic equation, which shows the individual ions that participated in the reaction and the formation of the precipitate. In the event that both reactants and products are all strong electrolytes and all the ions in solution are spectator ions, then there would be no net ionic equation and no reaction would take place. So we would show the ionic equation, the ions would be on the same on both sides, they would all cancel out, and you have no net ionic equation. So we have a few examples of something like that here in a second. Okay, so let's keep practicing. The best way to learn this is to practice, practice, practice. In our first example, we're mixing sodium nitrate and copper sulfate together. So the first thing we want to do is write out our balanced molecular equation and determine if a precipitate is likely to form. So we take NaNO3, which is aqueous. We react it with copper sulfate, copper 2 sulfate, CuSO4, which is also aqueous. And we are going to form our products. So we're going to take our anions and we're going to switch them. So what does that look like? Well, we have Na plus, NO3 minus, Cu2 plus, SO4 2 minus. I'm taking sodium and it's going with sulfate, and copper is going with nitrate. So we end up with Na2SO4 plus CuNO3 2. So I've rewritten those equations to account for their charge balance, right? Because sulfate has a 2 minus and sodium has a 1 plus, copper has a 2 plus, and nitrate has a 1 minus, which I didn't write there. Okay, now we want to balance this. I think all I need is a 2 out in front of my sodium nitrate to balance out the 2's on this side. So we are balanced there. And then our next steps are to utilize our chart to determine if a precipitate is going to form. So take a second, go back to your chart in your lecture guide, and determine which one of these is going to form a precipitate. The rules dictate that sodium, group 1 ions, and sulfate all are soluble in water, so this would get an AQ notation. And then we have copper nitrate. Well, nitrate we know is always going to be soluble in water. That's one of the ones that we got to keep in our brains. Okay, it doesn't have any exceptions, so this will also be aqueous. So no precipitate is going to form. This means that all ions are spectators. So they would both cancel out on both sides. They would all cancel out on both sides. So all ions are spectators, no precipitate is going to form. There was overall no reaction between these solutions. So nothing happened. Our next example is barium chloride mixing with potassium sulfate. So pause your video and try this one on your own. Start to become independent on your own of working through these problems, creating or predicting your products, determining what's going to be a precipitate, and writing out those individual equations. a reaction between barium chloride and potassium sulfate creates barium sulfate and potassium chloride. If forming those products is not what you had and you have your ratios incorrect, just remember to think of what the charges are from both of these reactants and make sure you're writing the formulas correctly. We can balance this equation. We have 2 there, and I think that's all we need to balance our potassium and our chloride. So now we can reference our chart to see which one was going to form a precipitate. Chlorides are going to be mainly water soluble. The only exceptions are a few metals, silver, mercury, and lead. So this one is going to be aqueous. And barium sulfate is going to be generally soluble in water, but one of the exceptions is barium. So barium sulfate is going to be our precipitate. Okay, so our next step is to write the ionic equation. So we're going to write everything with an AQ, which I forgot an AQ here, there we go. Write everything with an AQ as its individual ions, making sure to balance. So here we're going to have barium 2+, aqueous, plus 2Cl- aqueous, plus 2 potassium pluses aqueous, plus a sulfate 2- aqueous. That creates barium sulfate. We keep that together because it's our solid, plus 2 potassiums and 2 chlorines. Okay, that is our ionic equation. Our aqueous product is KCl, meaning that K and Cl are going to be our spectator ions, so they cancel out, and our net ionic equation is Ba2+ AQ plus SO4 2- AQ creates BaSO4 solid, and that is our net ionic equation. Let's try one more. So let's mix iron chloride, iron 3 chloride, and lithium hydroxide and determine if a precipitate forms, and if so, writing out the ionic and net ionic equations for that reaction. So try this one on your own as well. Here is our balanced molecular equation, and we do have a precipitate that forms, and that's iron 3 hydroxide. Hydroxides are typically insoluble in water, and iron is not an exception to that rule, so we have iron 3 hydroxide as our precipitate. Our ionic equation, I should say, is going to look like iron 3+ plus 3 Cl- plus 3 Li plus 3 OH-. And that creates iron hydroxide, which we keep together because it's the solid, plus 3 Li plus 3 Cl-. And we know from our aqueous product that lithium and chloride are going to be our spectator ions, so our net ionic equation is going to be iron 3+ AQ plus 3 OH- AQ goes to iron hydroxide solid. Our next example comes from our ALEX homework. We want to complete the table by deciding whether a precipitate is going to form between our aqueous solutions A and B. If a precipitate will form, enter its empirical formula into the last column. So what we're going to do is take our two solutions and we're going to swap their anions. We don't need to worry about balancing them because a balanced equation doesn't tell us if a precipitate is going to form. We just need to know what the product is and compare it to our chart in order to tell us. So we're going to swap our anions and compare it to our chart to determine if a precipitate will form. So we have copper 2 nitrate, so that's CuNO3 2, reacting with ammonium sulfide, NH4, but sulfide has a 2- charge, so that would be 2, and sulfide is just sulfur, sulfide. So those are our reactants. We're going to swap our anions and we're going to be left with NH4, NO3, and CuS. Copper has a 2+ charge, sulfur has a 2- charge, so they balance each other out. Okay. We know that ammonium and nitrate are always going to be water soluble. We've seen many examples of that in our lesson today, so this is going to get an AQ. We then need to reference our chart about sulfide. Sulfide is typically water soluble, but copper is one of those exceptions to the rule. So this will form a precipitate. So for this one, does a precipitate form? Yes. And what is that formula? CuS. And make sure you're putting in the empirical formula, which is the simplest form. Okay, our next one is ammonium nitrate, NH4NO3, plus potassium hydroxide, KOH, and we form KNO3 and NH4OH. NO3 and group 1 ions are going to be aqueous always. Hydroxides are typically water insoluble, but because it's with an ammonium, it is also an aqueous solution. So the ammonium kind of wins out there. So will a precipitate form? No. If you say no, then you don't even need to write anything in the empirical formula side. You just leave it blank. Our last example is going to be zinc sulfate. Zinc has a charge of 2+, sulfate has a charge of 2-, so we have ZnSO4 plus iron 2 iodide, so we have FeI2, and that is going to create zinc iodide plus iron sulfate. And we can see from our chart that neither of these are going to form a precipitate. Sulfates are typically water soluble, as are iodides. They only have a few exceptions, and iron and zinc are not one of those. So this will not have a precipitate. So again, you would not write anything for the formula there. So only one of our examples here formed a precipitate, and that was copper sulfide. Our last example is also from our ALEX homework, and it's asking us for the following chemical reaction. It takes place in aqueous solution. Write the net ionic equation for this reaction. Now you could sit here and write out the ionic equation, find what the spectator ions are, and then cancel them out, and then find the net ionic equation. But there is a shortcut that you can take. Because you know the net ionic equation is going to be made up of the ions that form the solid, since we're given the balanced equation already, all we have to do is say, okay, here's what my product is going to be of my net ionic equation. What ions came together to form that? Well, we needed a CO3 2-, and it was aqueous. That came from here. Okay, I only need one of those. And then I need a silver, but I need 2 of them because of the 2 here and because of the 2 here. So we have 2 Ag pluses. So for these problems, when you see them, you don't have to go the whole route of writing the ionic and the net ionic equation. If we're just looking for the net ionic equation, you're given the balanced reaction, just identify what the solid is and what ions would be needed to make it up, and just make sure you are balanced properly. So that ends our first lesson on aqueous solutions, reactions in aqueous solutions, and precipitation reactions. Our next lesson will cover 2 additional types of reactions that happen in aqueous solutions.